Bonjour, Madame et Monsieur. Thank you for the JEC organizers for the opportunity to speak today to you. I'm working for company UBE. We are a nylon producer, and I would like to get a little bit controversial today. Is the future only battery electric in the alternative drives in the mobility? Obviously, my position is not, but I wod like to tell you why. Okay, something is wrong with the screen. Here we are. So let me take you to a short journey around FCV and battery electrical vehicles and the technology behind it and the solutions and the risks involved. Let me go quite fast. 20 minutes is not plenty of time. And then come to a conclusion at the end of the presentation. So I picked here two very typical cars that are out in the market. The left side is a BMW EX series, and the right side is the Toyota Mirai. Of course, both cars are in the end electrical. When we talk about electrical vehicle or FCV, that means fuel cell vehicle, at the end of the day, the drive itself is electrical. The question is more about the chemistry. So we are talking about electricity in both vehicles, but at the end of the day, about the difference in the chemistry. And yes, both are silent as well and sustainable, because as long as the electricity is coming from renewable source, we have two very good solutions for future mobility. But on the other hand side, you can see I depicted the tank, which is not so nice in these times, but to showcase the problem with the electrical car. It's super heavy. We are having a lot of material involved. We come down to a 2.5-ton car, while the FCV car is, from the beginning, in the technology that we have today, 600 kilo lighter here in this direct comparison. On the other hand side, you have the problem with the charging. Everybody knows that. Even the fast supercharging take you like 30 minutes, 40 minutes to have 80 or 90% back in the battery. The hydrogen car obviously has a big advantage. You have much more range. According to WLTP, and you can refuel the car very fast. And on the other hand side, just to keep this in check here, the hydrogen costs are quite in check to this moment. I will not talk about the hydrogen cost from various sources today, but obviously there's a lot of literature also around this. So two good solutions, so far so good. Why don't we see so many FCV cars in the market and on the street then? So okay, then let's have a look at this one. Okay, we already discussed, we have two types of electrical technology at the end of the day, but the difference in the chemistry. And the difference in the chemistry gives you a difference in the well-to-wheel consumption. So apparently the battery electrical car is giving you a great advantage in the conversion ratio of the energy you input in the car, and that is directly coming from the electrical network or from your solar system on the house, and you convert, the conversion ratio is the best. It's an excellent conversion ratio of energy. And obviously, the hydrogen, first of all, has to be produced, and then you create also a lot of heat in the FCV stack when you drive, when you create the energy, the electrical energy that you need for your electrical motor. So there's a lot of data out there in the literature. I picked this one because it starts from the primary energy. And we have a difference of, the factor is around 3. So the battery electrical car is converting the original energy to a factor 3 better than the hydrogen car. But on the other hand side, I want to show you the blue part of the slide on the upper right side. And we have a completely different energy density. And that is the chemistry. This is the difference in the chemistry. H2 compressed chemistry delivers in a 10 kilo of compressed H2 the same amount of energy that you expect to have in a car, in an electrical car, like a Tesla S, for example. 85 kilowatt hours is round about the capacity of a decent battery electrical vehicle. So we have dramatically higher energy density in the hydrogen, and that lead me to the following intermediate conclusion. It's a little bit like wind and solar used to be in the past. 20 years ago, wind power was all over the world, and it was very efficient and successful. On the other hand side, I was myself in the solar industry 20 years ago. Everybody said, no, it's too expensive. The semiconductor technology is simply too expensive, the efficiency is too low, the conversion ratio is not good enough, you need a lot of area. And yeah, it was like nobody really, I mean, apart from the real believers, nobody in the broader market believed in this technology, and look at where we are today. So what I want to say is that the battery electrical vehicle and the hydrogen vehicle are complementary, same like the wind and the solar. It's as complementary as it could be. So we are talking about the electrical vehicle. They are silent. We can utilize renewable source energy, but the difference is in the chemistry, and the chemistry gives you the advantage and disadvantage on both sides. So now let's have a look more at the technical side of the things. I spare you with talking about the components of a FCV car. I assume that you might be aware, more or less. And of course, one of the heart is the hydrogen vessel. And then we come straight to the don't want to have situation. So the left side situation is a situation that you don't want to have. You don't want the vessel to burst. And on the other hand side, we are coming later to this in a deeper way. Here, for example, you have the tanks that are storing hydrogen have to have they have to be tested in a very extreme way. For example, just to this is a Toyota video, by the way, a Toyota official video. You can see that they even shoot a bullet through the vessel, and then they have a look at how the vessel is degassing. So let me show you the video. So see the bullet going in. You can see that it creates a lot of dust, and automatically the vessel starts to degas. So this is a very severe test. I wonder, we do this with a fuel tank. Nobody is shooting into a fuel tank. So we are shooting here into a hydrogen vessel just to make sure this thing works and this thing is safe, and I will come a little bit back to this. So, but is a battery electrical vehicle totally safe? So let's have a look at components. Again, let me spare you with the components. It's pretty clear. It's just for the totality of the presentation. That is a situation that you don't want to have in a battery electrical car. So what happens in the lithium-ion battery when you overheat? When you overheat, in the end, you create the left nice picture, and it's a nightmare for the fire guards. It's a nightmare because then you have to come. Now the fire brigades here in Germany, for example, they have a special container that has gallons of water, and they drown, when the car burns, they drown it in the water for 24 hours just to cool the battery off so long, and to stop from reigniting the battery. Yeah? It's a massive problem. We all know this. We have seen the pictures in the news. Yeah? So then, on the other hand side, let's have a look at the material solutions and who is UBE at the end of the day. So let me go from our company. We are a Japanese company. We have around 10,000 employees, and we are located originally in the south. Of course, we have headquarters in Tokyo, and we have Yeah, we have several different type of business segments. This has already changed a little bit. Sorry, this presentation is not 100% up to date. And I want to guide you to the chemical side, and from the chemical side, more specifically, to the nylons we are producing. We are a nylon producer, not only in PA6, we are also in PA12. That's why we have a lot of exposure in the automotive market, and we have all sorts of polymer combinations in between. So low crystallinity combinations of 6 and 12, of 6 and triple 6, 6 and 6, and even a combination, a Terpalex, we call Terpalex because it's a terpolymer of 6, 6, 6, and 12. We are producing these nylons not only in Japan, we are also producing in Thailand, in Europe, in Spain, and we have compounding plants all over the world. So our footprint is basically all over the world, and we supply our materials in a consistent, let's call this global grade supply way. We are coming from the PA12. We are very strong in the fuel tube market, but the fuel tube market is a dinosaur in the automotive industry now. And of course, I just want to show you this in order to give you a perspective where we are coming from. So we are deeply involved in the automotive industry. And when you come to battery electrical material solutions, starting from the nylon 12 or engineering plastics, of course, you immediately go into another type of tubing, coolant tubing, ethylene glycol resistance, refrigerant resistance, hydrolysis resistance. Yeah, I'm not sure whether you have any interest in this topic. We can talk about this later. We have our booth here, the booth of our company. So you're more than welcome to, if you're interested in this topic, you're more than welcome to talk to us. So more interesting. Okay, I spare you with the coolant tubing here. And let's go to the FCV materials. So, okay, intentionally I do not start from the materials itself. What I want to familiarize you with is more the way in this industry to create a pressure vessel that can take a 700 bar working pressure and 820 to 840 bar loading pressure. So, like I said, you don't want to have situation. That means it's the burst of the vessel. It's an uncontrolled burst of the vessel. This is exactly what you want to avoid. And there is a lot of regulation out there from the UN approved GTR 13. I just put a couple of, a number of typical tests that are being performed. There are two most important tests. That's the hydraulic test that you can see here. And the test is so harsh, so brutal, that you do this in a bunker. Typically, you do the testing in a bunker setting, or if you don't have a bunker, some people have rooms where they put steel plates, 2 millimeter, and you can really see the scratches in the steel plates after bursting. It's really deep scratches. There's this energy when you burst. The vessel is so huge, it's unbelievable. It's really a big energy. And then here you have the cycling test, the hydraulic cycling test that is really bringing the vessel to the edge of what it can do. Yeah? It's very harsh testing, very brutal testing. I don't think in the polymer industry we have something else that is so brutal. Yeah? And on the other hand side, you have road performance testing. It's also a cycle testing. And you have, but I have to be fair, you do this with a battery electrical vehicle as well. You really put the thing in flames. Yeah? You do a fire testing, but it's a very harsh fire testing. And here, different to a battery electrical vehicle, or a fuel tank in the combustion car, you really have to have the venting. So there's a The TPRD venting is you have the valve, and because of the fire, logically the internal pressure is increasing, and then there should be a controlled venting of the hydrogen. This is a very important point. That is what you do when you want to know you can create, or you did create, a good vessel that is up to the certification of GTR. And I just want to show you a little bit how deep we go in this industry for the FCV car. Yeah? On the other hand side, what's the material requirement? The first and foremost material requirement is barrier to hydrogen, nothing else. Yeah. So, okay, which material gives you a really good barrier? There have been all sorts of HDPE vessels out there for low pressure, for CNG, for example, or LNG, where you have a much bigger organic molecule than H2. H2 is very small. It's a very small molecule. It has the order number 2, so it has a very small molecule. And not a lot of materials, of polymer materials, are having a good barrier to hydrogen. And nylon is the material that gives you an excellent barrier to hydrogen. And on the other hand side, you have to mold. You have to mold the material. Obviously, the material is also modified. It's not a pure. We come a little bit later to this. It's not a pure PA6 or nylon. But it's a modified material, and you need to mold it. And now it depends on which type of player you are talking to in the industry. Some people are more familiar with blow molding. Other people are familiar with injection molding. Some people are really good in welding. But for this industry, for the molding industry, I put this a little bit controversial here. Because at the end of the day, I'm saying melt and weld. In some sort of way, you have to create a melt, and in some sort of way, you have to weld. And the funny thing is, you are not coming out of this situation without welding of some sort. You only have to widen your perspective. What is welding? And at the end of the day, what you need to create is, you need to create a consistent matrix in the molded part. And whether this is a weld or this consistent matrix is coming out of the melt, in the end, it doesn't matter so much. Yeah? So let me give you an example. We have the chance, for example, with HDPE in the multi-layer. There's other good barrier materials that are, however, very brittle, EVOH, for example, and you can theoretically produce a multi-layer approach HDPE, like you have in the food industry, for example, or also in the fuel tube. Yeah? So you can create a multi-layer. But then you have the problem when you quench the multi-layer in some sort, either by blow molding or by injection. How are you sure that the barrier layer is interacting from the one side of the mold and the other side of the mold, or of the pinch-off? How do you do this? Very complicated. It's not a good solution. So let's go with the monolayer. Then, of course, you can work in the rotational. Yeah, there's the very nice sintering material in PA12. Very, very easy. You know, you can go in rotational molding. That's fine. But in the rotational molding, how much pressure do you apply to the melt to get a consistent matrix? And I just put a few things here that are important to be reproduced on the industrial scale. Yeah? So you need to be careful of your dimensional distribution variation. You need to have a look at where your chains, the polymer chains, are orientating. Hopefully not. Less orientation is better. Crystallization is essential also for the hydrogen barrier in the end. And the residual stress will create, if you have stress in the part, you can anneal, but if you have stress in the part and you create a tank, then at the end of the day, when you go into the bunker and you do all the cycling testing, you see the fracture. It will come because you have the stress in the part. Yeah? So then the question is, how can you make a very nice part with a low amount of stress under these circumstances, because in some way you have to have a weld, and in some way you have to have a melt, and out of the combination of melt and weld is bringing you to the good part. That is making the good part, and the most important thing is the reproducible part, not a lab good part, an industrial good part where you can produce 20,000 pieces on one machine a year, or 50,000 pieces on one machine a year, okay? So that is, from our side, the most important point, and we are professional in this. UBE knows how these things work, and we are supplying our PS6 for monolayer. We believe that the monolayer is the right thing to do, not a multi-layer, and we believe that the PS6 is, in general, better than the long-chain solution. So I'm running out of time. I'm giving you now two examples. We have here a low viscosity grade with a good barrier, here on the lower side, and of course modified so that we have a good Sharpie performance in the very low temperature range. And you can see this is what I talked about. If you inject, you weld. You weld by some sort of way. IR welding, or there are all sorts of welding that you can apply. So on the other hand side, we are also working in high viscosity, high melt strengths for blow molded tank liners. Okay, so then let me go quite fast now. Come to the end of the session. So let's have a look at the infrastructure out there. Will the FCV car come? And look at this growth rate. I just put here this very nice H2 refill network. It's growing very fast. You know, this is a consortium. For example, only H2 mobility is only in Germany, but we see the growth of refueling stations all over the world. And on the right side, you can see the consumption is real. The consumption is going up from less than 5 tons to more than 25 tons over 5 years. So if we can continue this growth, we will see more FCV cars to come. On the other hand side, we have a lot of electrolyzer capacity coming from renewable energy, creating green H2. Yeah? And the announcements that we have today create enough 170 kiloton of hydrogen. That is enough for 1.7 million cars running at 10,000 kilometers a year in FCV, okay? So that's the announcements on the table today for new capacity. So hydrogen is there, and the cars, you can see here the car sales. 2021 is only the first half. So adding the second half is dramatically more. So it's still rare. We still have a rare number of cars, but the growth rate is outpacing all other alternative drives growth rate. So we will see more FCV cars in our streets. Yeah. So okay, then in FCV we have the high energy density, fast refuel, long distance driving, and so then hold on tight, I would say, for the FCV car. So let's keep the vessel together. Yeah. And on the battery electrical vehicle, we have an excellent well-to-wheel ratio. We need to keep this in mind. But a low energy density and short to medium distance driving. And for the battery, I would like to say, stay cool, don't flame. And that's the end of my presentation. Thank you very much for your attention. So 1 minute for questions, if you have. Nobody there? Please, one question, please. Okay, we are good. So please, if you have any more questions that you don't dare saying now, please come to our UBE booth. You're more than welcome. Thank you very much.
We're going out on our first date. You and me are thrifty, so go all you can eat. Fill up your bag and I fill up a plate. We talk for hours and hours about the sweet and the sour and how your family is doing okay. And leaving, getting a taxi and kissing the backseat, tell the driver